Okay, today we're going to be doing the Diode Lab 2, Part 2. We did Part 1 last time. And this is the document, the experiment document, the Diodes Lab 2. And it has all the explanations step by step, which I'll be going through here. So it will be useful for you to have a copy of this with you when you watch the video to do the lab. I have some screenshots and so forth in here. I will provide you with graphs, but you may want to have this document so you can follow what's going on as I go through the lab. You will then fill out the lab report document, and then this is what you will turn in for your grade. On here it says you are to attach printed graphs. However, you do not have to print out graphs and attach them to your report. I will give you copies of the graphs so that you will see what they look like and to help you to answer the questions for your lab report. There's no calculations for you to do in this lab. So here's the components we're going to be using. I have four 1N-4007 p-n junction diodes. That's the same diode we used in the last lab. We also have a red LED, and I have three resistors. The first one here, we have a brown, black, red. The first two stripes, of course, are the first two digits. Brown is 1, black is 0, so that's 10. Red is 2, so that the third digit, of course, is the times 10 multiplier. So red is 2, so that's 10 to the second power, which is 100. So 1, 0, which is 10 times 100 gives me 1,000 ohms. This one we have an orange, orange, brown. Orange is 3, so that's 33 times 10 to the first power, which is 330 ohms. Then we have a brown, black, black. Brown is 1, black is 0, so that's 10. 10 times 10 to the 0, which is 1, so this is a 10 ohm. Then I also have a 100 microfarad capacitor and then two connecting wires. So here's our electronics kit. Here's the PASCO interface, some connecting wires, and then I have two of these voltage sensors that plug into the analog inputs on the interface, and then that will connect with the computer. I have the circuit all set up now. I have my diode here. This is the 1N-4007 p-n junction diode with the cathode on the left side, connecting wire between these 2 points, and then I have the 1K ohm resistor. Here I have a voltage sensor connected to channel B that monitor the voltage across this resistor, and then I'm going to add another voltage sensor to channel A, and I'm going to put that across the diode so I can monitor the diode voltage. So I put the red one on the high side and the black connector on the low side. Okay. My input signal from here is going to be a 2 hertz 3 volt sine wave this time. Where in the Diode 1 lab we just ramped up a voltage, but this time we're going to input a sine wave and we're going to watch what happens. I'm going to have to move the camera over to the video display on my computer and change the settings on my camera, otherwise you won't be able to see the screen on the camera very well. So I'll pause here while I readjust the camera. Okay, now I've got my Capstone software started up, and I've loaded in the activity P54 Diodes Lab 2, Rectifier and Power Supply. The first page of the workbook just gives a description, and the second page shows the options. We have a signal generator function set to sine wave with an amplitude of 3 volts, frequency of 2 hertz, and we're in the fast monitor mode. Then on page 3 I actually have an oscilloscope display, And the circuit is set up, and I clicked on this button down here at the bottom, and I can start monitoring the data. And you may not be able to see it very well on the screen because the contrast is not real high on the oscilloscope display, but I have time axis here on the horizontal axis, voltage on the vertical scale, and so I get an actual oscilloscope display. After I get a few peaks in here, then I can stop, and I've got a few peaks in my circuit. So to help you see it better, and also so I can save the data, we're going to make a graph of this data. So I highlight the first channel I want to look at, and up here is a snapshot tool. If I click on that, that takes a snapshot of that data. Then I highlight the other one, and I take a snapshot of that. And then I'm going to go over here to the data summary and click there. In my voltage channel A, I can change that from snapshot. I can rename it. Click on the gear icon, and I can rename this one. Channel A is the diode voltage. So I name it diode V. And close that window. Then I go to the channel B snapshot. Click the gear icon, and I can rename this one as the resistor voltage. Resistor voltage. Okay. So now I have those renamed. And over here I have a graph tool, so I'm going to open up a new workbook page. I click there. I have a new page. Open my data summary. Grab the diode voltage and drag it over here to the graph tool. And I've got a graph of my diode voltage. Now I can go down to my resistor voltage and drag it onto the graph, and it plots that one as well. So now I've got both of those plotted. Close my data summary window. And so now I have a graph of my data. I could move the legend down toward the bottom. And now you can see what's going on with my data. See, I've got, let me try to center these peaks in here. I'm going to get, I can drag the scale down. There we go. I can center that. So you can see the red one here is the voltage across the diode. And you can see that when the signal, which is a sine wave, I have a sine wave at 2 hertz, when that starts to go positive, the diode turns on. And as soon as the diode turns on, the voltage across the diode stays flat. Right? And that is at the turn-on voltage. So I have 1 volt up here. If you recall, the turn-on voltage for the diode was about 0.6 volts. So I'm just a little bit above halfway, so that's about 0.6 volts there. And as soon as the diode turns on, this graph, the green one here, shows the current through the resistor. So now I get current through the resistor. When the voltage goes negative, now my diode turns off and I have no current. So I have the flat green line at 0 or across the resistor. So I have no current through the resistor, then I get current through the resistor. So the current is only going in one direction. When the voltage reverses polarity, I get no current through my circuit. So since I have DC, so I have current in only one direction. But I don't have a true DC because it's not flat. Right? True DC, like from a battery, I would have flat across the top, and I don't have that. So I still have the humps here. So my current still varies in time, then it goes completely off for half the cycle, and then I get my current back when we switch back to positive. Okay. So I'm going to give this graph a title down here as single diode. Oops. Yes. So I've got a graph title. I've got my resistor voltage, diode voltage, so this graph is ready to go. Now I could just print this off. And normally if we were doing this in the lab, I would have you print this off and attach it to your reports. But instead of doing that, I'm going to save this data as a picture. So what I'm going to do is, I'll try to center these peaks a little better. in the screen. Now it's ready to go. So I'm going to take a screenshot, and then I'm going to open up a PowerPoint slide, a blank PowerPoint slide, and paste it. And so I have it pasted in here, and then after I get all the graphs pasted in here, then I can save them as JPEGs and edit it down so I just have a picture of the screen, and then I'll post that on Blackboard for you all. Okay, so we'll go back to here, and now we're ready to go to, we're going to switch a component. We're going to take out the diode and put in the red LED and see how that looks. So I'm going to pause the video here. All right, now I've changed the diode out with a red LED, and so we're going to run it again with the red LED instead of the diode. So I click my monitor to start running, and then after I get a few peaks in the screen, oops, I kind of missed a little bit there, so I'll do it again. Okay. So now we're going to make a graph of this data. So highlight that, click the snapshot, highlight the channel A, take a snapshot, and I go to the data summary. My monitor runs snapshot for channel A. I'm going to rename that as the LED voltage. And then go down to the channel B, snapshot data. Computer's being slow here. There we go. And then now I got resistor voltage. Okay. So now that I have snapshots, I can open up a new workbook page and make a graph of this one. So I grab my LED voltage over to the graph tool, and then I grab my resistor voltage and drag that onto the graph. So now I've got both of those. So I'll close this window. Now we can see. Let me drag the legend down towards the bottom, and we can see the peaks. Okay, I'm going to stretch it out here so we've only got 2 peaks in the display. Try to center it. Okay, this one looks quite a bit different now, doesn't it? We still have here, the purple one here is the LED voltage, and we get the flat top again where we get the turn-on voltage, but it's much higher now. Look, it's up here close to 2 volts. So if you recall, the red LED had a turn-on voltage of about 1.87 volts, right? Where the regular diode had a turn-on voltage of about 0.6 volts. This has a turn-on voltage of about 1.87 volts. And so the turn-on voltage is much higher. Since I have a higher voltage drop across the diode when it is on, I've got far less current in the circuit. So my current peaks are much smaller. This blue one here is actually the voltage across the resistor, which is proportional to the current. And so I have much less current in my circuit because of the higher turn-on voltage for the LED. And so, but again, see how I still only have current in the forward direction, and then when the polarity reverses, I get no current. But since I have a much higher turn-on voltage, the LED doesn't turn on until much later, and so I get far less current in my circuit. Okay. All right, so that's the end of this portion of the lab, and so the next part is part 4. This was part 3. Part 4, we're going to look at making a power supply, a DC power supply. So we'll pause here and change our circuit out. Okay, now we're ready to begin the last unit, which is Unit 4, called Power Supply. And so we only had to make some slight changes to our circuit. So I have the 1N-4007 diode with the cathode on the left, connecting wire here, and our load resistor now is going to be 330 ohm resistor. So it's a simple series circuit, but I removed the channel A voltage sensor, which monitored the voltage across the diode. We don't need to monitor that one now, so we're just going to monitor the voltage across our load resistor, which also gives us the indication of the current, since the current is proportional to that voltage. Our input signal is still going to be a sine wave, but we're going to bump that up to 60 hertz. 60 hertz is, of course, what we use in our homes and businesses, so when you plug something into the wall, you get 120 volts at 60 hertz. But we're going to keep our amplitude at 3 volts like we did before and just increase the frequency to 60 hertz. And so I'll set up the computer and then switch the camera over to there, and we'll see what the signal looks like. All right, here we're back to the program, the Capstone program. So I go into the hardware setup and I remove the channel A voltage. So now we're just going to monitor the voltage on our load resistor, and we're going to monitor the output voltage from the interface, which is the 60 hertz sine wave we're supplying to our circuit. And then in my signal generator, I modified the frequency up to 60 hertz, still 3 volt amplitude. And then I click on the axis title for the vertical axis, and then I can check to make sure I'm monitoring both the voltage on channel B and the output voltage at the same time. So everything's ready, and I can start monitoring my data. Now I had to adjust the time scale. So before we had the time scale something like this, right? But since we went up to a higher frequency, now I can just click and drag, and I can get multiple peaks. So I got enough peaks in there. I click stop, and now I'm going to, you can see the purple here gives me my 60 hertz sine wave, and if I click on this one now, you can see our diode rectifies that 60 hertz sine wave. So we only get current through our load when the voltage goes positive. When the voltage goes negative, the diode blocks the current, and so we only get current through every half cycle. Alright, so we're going to save that diode voltage, so I take a snapshot of it, and then I go to the data summary, and my monitor run snapshot. We're going to change the name and call this one rectified voltage. So rectified B, and I'm going to save that. Okay, then we're going to open another workbook page, and I'm going to take my rectified voltage, drag it over to the graph tool, and now I have a graph of my rectified voltage. Okay. Alright, so next we're going to add another component. This time we're going to put in a capacitor. So I'll stop right here and change my circuit. Okay, now I'm going to take my capacitor. I have a 100 microfarad capacitor, and we're going to put this one in parallel with our load resistor. So I can just push into the springs and connect that one in parallel. Okay, so now I have the capacitor in parallel with my load resistor. Then we'll go back to the computer screen and we'll start the voltage and see what happens with the capacitor in place. Alright, now I have the capacitor hooked up in my circuit. I'm going to start the run again. So I click on monitor. And now I got some peaks. Let it go for a few seconds. Stop. And now we can look at the voltage now. So you can see we got this little different pattern than we had before. So I'm going to snapshot that data and then go over to data summary. And my snapshot, I'm going to rename this one as filtered voltage. Okay, then open a new. Now I'll go back to my previous graph I had before, and I'm just going to put this one right down below. So I'm going to drag it underneath the graph. A little box opens up, and I put it underneath there. So now I have this. Now look what happened to the peaks. Let me close this here. I stretch this out a little bit, and I adjust the scale. Put 0 at the bottom, 3 at the top. Okay. Now it's a little bit crowded in here with the reading time here and time here. So I go up to the gear icon, click on that, and on the axis appearance, on the axis labeling, no, not there, where is it? Display, show all axes. No, uncheck that. Okay. So now I just have the time at the bottom. The two time scales are the same, but I only need one label. And I have 0 at the bottom, 3 volts at the top, and then I do the same thing with this one. Put 0 at the bottom and adjust this. So now they're on both the same scale. Now look, with just the filtered voltage, with just the diode and the load resistor, here's my half wave. But now look what happens when I put in the capacitor. The capacitor tends to try to flatten it out. So you notice that. Let me adjust this out a little bit here. As the voltage increases, my capacitor will charge up. And then when the voltage starts to drop off, the capacitor will discharge and dump its charge back into the circuit and try to keep our current up. So now we're getting more of the flat line like we would have in true DC. So adding in the capacitor will charge up as the voltage rises, and then as the voltage drops, that capacitor dumps its charge back into the circuit and tries to keep the current up. Right? So we get more current through our load this way by putting in the capacitor. So when the voltage drops, the capacitor discharges and tries to deliver more current to our load. Okay. So remember that we're trying to supply energy to some load, and the energy that we supply, the rate energy is supplied, is proportional to the current. So the more we can keep our current up, the greater the rate that we supply energy to our load. So putting in that capacitor now, as the capacitor charges up and then discharges, it tries to keep that current up and deliver more current through our load. Okay. So now we're going to add another load. I'm going to add in a 10 ohm resistor in parallel to simulate driving some other circuit, or say an electric motor or something. So we're going to add a low resistance load and see what happens to that. Okay, now here's my 10 ohm resistor. So now I'm going to stick this in the component springs. So now I have an additional 10 ohm resistor in parallel. So that's going to simulate a low resistance load, such as an electric motor, or it could be simulate some other circuit that we're trying to drive. Okay. So now the circuit's set up. We'll go back to the computer screen. Okay, our circuit is set up now, so I'm going to start monitoring data again. And now after we get a few peaks, let it go for a few seconds. Click stop, and now I'm going to take a snapshot of this new data now. Click the snapshot, and now I'll go over to the data summary, and my snapshot data, I'm going to rename this to load resistor. Alright, so now we have all the parts for this one. So now I go to page 4 where I have my graph, and I'm going to add the load resistor voltage to the bottom of this. So open up my data summary, grab the load resistance data, drag that to the bottom, and now I've got all the graphs on one. So I'm going to adjust the Y scale so they're all the same. So I drag this down. So 0 at the bottom, 3 volts at the top. So now my vertical scales are all the same, and my horizontal scales, my time axis, are all the same. So we'll stretch this out to get all the peaks in. Okay, so the top one, of course, is just our rectified voltage, which is a single diode and a load resistor. Then the second one in the middle is filtered. I've added the capacitor in, and you can see the capacitor discharging, and the circuit tries to keep the current up. But now look what happens when I go down to my load resistor. By adding the 10 ohm resistor in parallel, you can see the capacitor discharges much faster. So the discharging capacitor discharges much faster since the resistance is so much lower. So, but I'm still supplying more current to my load than I do without adding the capacitor in. So we have current through our load, but then we still have these gaps where there's no current through the load. So we're still not very efficient at supplying energy to our circuit. Right? But this is the end of this part of this unit, and now we're going to build a diode bridge and watch and see what changes there. So I'm going to pause the video and get prepared to build the diode bridge. Okay, now we're ready to start the last unit of the last part of Unit 4, where we build the diode bridge, and so we get a full rectification. So I have the diode bridge set up here. We have a diode up the top with the cathode on the right, a diode here with the cathode on the bottom. We have a diode over here with the cathode on the bottom, and a diode here with the cathode on the right. I have a wire connection here to the positive input and a wire from here to the negative input. I have my load set up from across the diagonal between these 2 points, and then the voltage sensor monitors the voltage across our load resistor. So when our input is positive, we get current through here, down through this diode to this point, through the resistor from bottom right to upper left, then through this diode, and then out through this wire back to the supply. Then on the other half of the cycle, when this is negative and this is positive, the current comes in through this wire, through this diode, and again through the load from the bottom right to the upper left in the same direction, and then out through this out through this diode through here and back to the supply. So every half cycle I get a positive current through my resistor from bottom right to upper left. So when this is positive, I get a current from this direction, and when this one is positive, I get a current in this direction. So with the single diode, I only got a positive current through my load every half cycle. In the other half cycle, it was 0. Now, every half cycle, I get a positive current through my load. So this is a full wave rectified. So my time average current is now much greater because I'm not turning it off every half cycle. So now with the circuit set up, we're going to move the camera over to the computer screen and run the program and see what the waveform looks like. Okay, we're back to our computer screen now, but before I start this, I have a drawing here to show you what we're doing. So here's a sketch of our diode bridge. So here's our AC input from our interface, and when we're on the positive side of the sine wave, we follow the red path. We go through this diode, and then we go through our load resistor from the bottom right to the top left, and then out through this diode, and then back to the return. And then when we get the other half wave of the cycle, the bottom half here becomes positive, and then we follow the green path, come up through this diode, and again, we go in the positive direction through our load resistor from bottom right to top left, and then out through this diode and back to the return. So no matter what the polarity of our source is, every half wave we still get a positive current through our load resistor. When we just had a single diode, we only got positive current through our load every half cycle, and the other half cycle was zero. But now, that other half cycle, we still get a positive current through our load resistor with this diode bridge. Okay, so we'll go back here, and we're ready to start monitoring the data. So we'll go ahead and click Start. Get some peaks in there, and click Stop. And now we can see I get a full wave rectified, right? Instead of going off every half cycle, here's the input, see, the sine wave input, and I go through my load resistor, and I get one every half wave. I still get a positive current through my load resistor. Okay, so we're going to highlight that data, and we're going to take a snapshot of it, and we'll go over to the data summary, and we'll monitor. Click on that one and rename this as full rectified. And then we've got that data saved. And now we're going to add another component. So this time I'm going to add my capacitor again. And so I'm going to pause the video while I add the capacitor. Okay, now in the circuit you can see I've added the capacitor in the same connections where my load resistor is. So my load resistor is right here underneath the capacitor in the same connection. So the capacitor is now in parallel with my load resistor. And now we're going to run it again and see what it looks like. Okay, now we're set up with the capacitor in parallel with my load. I start the signal. Give it a few seconds. Stop. You can see the sine wave on here, and we'll switch over. Now, look at our filtered voltage. When I look at the voltage across my load with the capacitor, we get nearly flat. Look at that. So now our capacitor, just like before when we had the single wave rectified, now with the full rectified, we get almost flat voltage across our load. So you can see the capacitor charge up and then discharge, charge up and discharge. So once the voltage starts to drop down, then the capacitor will discharge its charge back in the circuit, and it keeps the current up. And so the current never does go all the way down to zero. All right, so we're going to save that data. So I'll take a snapshot, and then I go to data summary, and I rename this one, and this is going to be filtered. Okay, then next we're going to add, oops, I want to graph this as well. So we better add another page. And the data summary, okay. My full rectified, I'll go over to graph tool. There's my full rectified. Now I add my filtered. Okay, and let's close that window. And now let's set the scales. Go up to the gear icon, my display appearance. I want to remove the extra x-axis. There we go. And this one I'm going to move here. Put my 0 at the bottom. now I have my y-axes are the same for both, and you can see better how I got with the filter in there, with the capacitor as a filter. I get nearly a flat line. I still have a little bumps, but nothing like this, right? So the capacitor is helping to keep my current up. Okay, so next we're going to add in another 10 ohm resistor in parallel with those to simulate a load that we're driving, just like we did for the half-wave rectifier. Okay, I've added the 10 ohm resistor in parallel with the capacitor and my other 330 ohm resistor, so that extra 10 ohm resistor will simulate a low resistance load like driving a motor or maybe some other circuit. And so we'll start monitoring the data. And I got my peaks, so we'll stop. And now again, in the green you can see the sine wave. And now, just like I did before, when I added that low resistance load, we can see that the capacitor is discharging much quicker. So that low resistance, the capacitor discharges quite fast. So we still get a little bit of extra voltage right here instead of going all the way down to zero quickly. So it's still better than without the capacitor filter at all, but you can get the idea of how we can actually convert AC into a true DC by adding these capacitors, because then the capacitor can charge up on when the voltage is increasing and then dump its charge back into the circuit to try to keep your current up. So, okay, we're going to save this data. And then we'll go over to the data summary and rename this. And this is going to be load resistor. Okay, and then we're going to add that data over to our graph. That's going to go on the bottom. Okay, so I'll adjust the scales. They're all the same. Okay, so my Y scales are all the same now, and my X scales are the same. And I've got all my labeling in here. And the graph title now is going to be full rectified voltage. Oops. Okay, so that pretty much completes this section for this lab, and I want to save a picture of this, so I'm going to take a screenshot, and then I go over to blank slide, and I'll paste that in. Okay, and close that. Okay, so now this completes the lab section, and again, I will edit those pictures and save them as JPEGs and post them on Blackboard for you. You do not have to print them out to include them with your lab report, but those graphs will help you to answer the questions for your lab report. So, all right, so that completes this one, and I will talk to you in another video.